And we'll begin the formal part of the event with acknowledgement of the country. So in the spirit of reconciliation, the Statistical Society of Australia acknowledges the traditional custodial country throughout Australia and the connection to land, sea, and community. We pay our respects to the elders past and present and extend that respect to all Aboriginal and Torres Strait Islanders peoples today. And it's my absolute pleasure to introduce tonight's speakers, Hanlin and Shang. Hanlin is the Professor of Business Analytics at the Department of Actuarial Studies and Business Analytics at Macquarie University. Hanlin's research interests including inference, modeling, and forecasting functional time series. So tonight's talk will basically give us a slice of that, and Hanlin will talk about the long-range dependent stationary functional time series. Hanlin, the floor is yours.
Okay, thanks, Thomas. I'd like to thank Thomas and Alex for organizing this event. It's absolutely delightful to be given this opportunity to present a talk. This is the first time to present this work, so there are some results that I hope to complete but may not. But it's good to get your feedback. So in this presentation, I will be looking at two problems. The first one is looking at the Sieve bootstrap, which is a new methodology for bootstrapping functional data, in my view. And then I will be using this methodology to estimate uncertainty associated with the memory parameter in the long-range dependent stationary functional time series. So I will begin by giving what's this talk about. So this is to construct confidence interval, pointwise confidence interval of the memory parameter. So we will consider just one memory parameter. So it's not multifractal. It's just one Hertz exponent or D in the autoregressive fractional integrated moving average. So those are the common memory parameters, but it's just going to be one scalar value. And the aim of today's talk is to looking at uncertainty quantification of the long-run covariance under stationary long-range dependence. So long-run covariance is like covariance in the ideal world, but when we have a time series data, we really should consider long-run covariance that consists of the variance as well as the autocovariance component. Now, this long-run covariance only works when we have stationarity. So I will restrict myself in the stationary world in the talk. So for those of you who may not familiar with functional data or functional time series as a small subset of functional data, I will give a little bit introduction before moving on to talking about today's topic. So the rise of big data is it's very important, and it's create a lot of problems and interesting ideas to explore. And this big data tend to come in fast speed and also big volume, and the varieties is the third V. This is where we have census data, where we could have survey data that have multiple sources. So those are the three V's. Now, functional data in the form of curves, image, shapes, or manifold. When we're looking at a function, we have a one-dimensional curve. We could have two-dimensional image, could be like satellite image, or shapes. You could look at a bone shape, or a manifold that beyond our visualizations. So manifold is, there could be Riemannian manifold that borrows the shape data analysis with functional data analysis together. Now, in this work, I will be focused on functional curves. That means my functional data are one-dimensional in the function space. And here I have a time series T. This is discrete. U here is a continuum, also known as continuous variable. And this belongs to a subset, oftentimes is 0 and 1. So it's a subset of real space. And the domain doesn't have to be 0 and 1. It could be any range. but we can always standardize to the unit interval. Now, when the continuum U is a time series or time variable itself, and this is the sliced functional time series where we have T as the time indices and the U also as another time variable. And the cross of the problem is to model the temporal dependence within and among functions. So by within functions, it's for each function, there are temporal dependence in the U variable if we discretize it. Now, there will also be temporal dependence in T because it's a time series. How does it differ from the multivariate or high-dimensional sparse VAR literatures, for example? It's because in the multivariate settings, the number of variables create problems. So we tend to use sparsity to help us shrink the number of variables to a manageable set. However, in functional setting, the more variables give rises to dense functional data, which in my view are the most easiest one to work with. So this is an example where we have a curve time series. By curve, I mean they live in one-dimensional function space. So this is the near infrared spectroscopy measurements over this wavelength. And each curve is measured at one given time point. So it's to do with wood panel compression, where they mix wood residuals with glue in the industry environment, and they compress the wood residual every 2 minutes until it becomes denser and denser to the timber we use for furniture. So over these 80 observations of functional curves, what they like to know is the optimal stopping time, and after which they don't need to compress anymore. The nice thing about functional data is we have the continuity, and this allows us to take derivatives. And the use of derivative information can sometimes give us a better inference than the original data alone. So functional data analysis tools tend to live in a Hilbert space. We tend to work with Hilbert space because it has inner product, but it can also be in Banach space. So it's a linear space. But if our functional data are constrained, such as PDF or CDF or Lorentz curve in economics, and they tend to live in the base space. So this is a nonlinear space, and where we have to respect to the constraint given in the problem. In the Hilbert space, we have the nice inner product, also our two norms or different type norms. And in the base spaces, one popular method we use a lot is the compositional data analysis. In particular, is the centered log ratio transformation for modeling the constrained functional data, such as PDF, CDF, and the Lorentz curves. And for example, PDF, they all have to be greater or equal to 0, and they have to sum to 1, and those constraints has to be respected when we're doing modeling and forecasting. Now, how do the functional data observe? They don't observe continuously, unfortunately. So what we like to study are 3 scenarios where they observe at different frequencies. So before then, I will just define a notation where we have a functional curve X and realize at a set of discretized data points. We have U1 to UK. Depending on this K value, we could have 3 scenarios. The first one is the high sampling frequency that leads to the dense functional data, and low sampling frequency leads to the sparse functional data, but we still can recover the covariance and the mean through kernel smoothing or other smoothings. And when we have no sample at all in a part of the domain, this gives rises to fragment functional data. In a sense, it's the hardest problem to solve, where we have absolutely no information and we only observe an interval within the functional domain. So in functional data analysis, we tend to care the most the mean and the variance because they give rises to Mercer's lemma and the KL expansion. So I will just talk about them as well. So we denote n as the number of curves, and we have sample mean. And sample mean is just like a simple mean we have in the univariate cases. And if you like U to be the population mean function, and then we can write down our population variance. And this population variance, we call it variance operator. And we can do the functional principal component analysis based on this variance operator. So if the data ID, this variance is the criterion we use for functional PCA. But if the data are non-ID, in the case of time series or spatial dependence, perhaps the variance criterion may not be optimal. And today I'll be talking on long-run covariance as an alternative. Now, there are one very important representation theorem, Mercer's one. This allows us to approximate reasonably well or exact of that variance operator. And this is given by the eigenvalues and the bunch of eigenfunctions. They're also normal. So this is give us the optimal representation to approximate this variance operator. Now, there's also another KL expansion, which says any realization in a function space can be approximated by principal components multiplied by principal component scores. And in practice, we don't take infinite many, nor we take up to n. So we take a smaller size L, which is far less than n. And in this way, we can do the dimension reduction. So I'm going to talk about long-range dependence. So this, before then, I will talk about a parametric toolbox. So in the existing literature, what we have is functional AR1. This is simply an extension of autoregressive of order 1 to functional data. And then we also have functional ARP, where the order is greater than 1. And how we determine the order of P, there are hypothesis tests that allows us to sequential test until we can't increase the size of P. There are also a functional version of moving average of its order Q. And then by combining AR and MA, there is a functional autoregressive moving average with order P and Q. So all those techniques above, they are parametric, and they designed for short memory. There is absolutely no long-range dependence. So in their functional ACF plot, you can see they decay really fast. So how do we see that? And we define the functional ACF. This is given as the norm of the autocovariance at lag L divided by the variance. So this gives rises to the autocorrelation at lag L. And then if you plot this autocorrelation against the lag variable L, this gives rises to functional coloregram. Okay. Now, I'm going to show you the functional coloregram for the long-range dependent. Before then, I will just start demonstrating using a numerical study here. So I will have long-range dependent data, and after taking the fractional order difference, and I will have a stationary data. So my original data is stationary, but it has a long-range dependence. After taking this difference, I will have a stationary data with short memory. And then I can apply the FARMA with order P and Q on the left and the right. Now, another thing I'd like to mention is the D parameter. I'm going to restrict that in the stationary world so that it has the invertibility and also a stationary. So my D has to be less than half to ensure stationarity, and D has to be greater than minus half to ensure invertibility. So this is captures the AR component, and this captures the moving average component. Okay. So when we estimate, there are two things that we care the most is the kernel function. So we have this phi and psi representing different kernel function in our AR and MA components. Now I'm going to define them shortly in my simulation. And in short, I need to make sure they are invertible and have the causal relationship. So I need to set some constraint on those two kernel functions. In my simulation, I'm also going to have a function support between 0 and 1. So that is in the unit interval. And eta t here is error term, which is standard Brownian motion. I'm going to consider two cases, represent FAR with order 1 and FARMA with order 1 and 1. To demonstrate, I will set d equal to 0.2. I will also consider other cases. In the first one, where I only have AR components, I will consider this representation, and I chose 0.34, this magical number. It's because I want to have the norm of the phi equals to 0.5 approximately. In the second case, I have the same for phi 1, and I have additional operator for the moving average component, and I chose 1.5 such that I also have the norm approximately equals to 0.5. Okay, so they represents the model rate dependence. So in this example, I have the functional calorogram with different value of d. As d becomes closer to the upper bound of 0.5, as you can see, we have a very strong dependence. After about 100 lags, there is no decaying to 0. So this is indication the presence of long-range dependence. As d becomes smaller and gradually towards 0, and this is converging to the short memory case. This dotted line is customarily the upper bound. It's basically computed at 1.96 divided by square root of n, where n is the number of curves. Now, the estimation of long-run covariance is very important. And how do we define them? Before we define the long-run covariance, I will basically use ergodic theorem and stationarity. By stationarity, I mean the mean and the covariance do not vary over time. And by ergodic, I mean if I have a long sample and I can approximate statistic reasonably accurate. So those are very standard. The long-run covariance can be represented here. It's really just a sum of all autocovariance with all different lags. Theoretically, from minus infinite to infinite, but in practice, we truncate it to a finite number in order to balance the trade-off between square bias and variance. Now, this autocovariance at lag L can be represented in terms of this covariance structure here, and then you can write down in terms of expectation. So this is the general formula for the long-run covariance. How do we estimate this long-run covariance? And more troubling, worrying is the fact that when we have a long memory process, the integral operator of this long-run covariance is now finite. So if we don't have finite long-run covariance, and what do we do? So and even more, how could we estimate this d parameter? Another feature is the norm of the autocovariance gamma L for different lag L will decay more slowly than the short memory counterpart. So this is the feature as I mentioned before. Now, if you have a finite sample, and especially when sample sizes are small, we need to worry about how we can estimate this long-run covariance reasonably accurate. And then a natural estimator is represented here, and alpha is our memory parameter. And if we have short memory, alpha equals to 1. And H is also known as the Hurst exponent. And then if alpha equals to 1, this is simply just 1 over n. And you can put this term inside this summation. And what's the first term here? It's just going to be a linear decaying weights. As lag L become closer to n, far away from 0, and we have less weights assigned to the corresponding auto covariance. So the long-run covariance is simply just the sum of auto covariance or autocorrelations. And then the important thing is how we estimate this alpha, or how we estimate these Hurst coefficients. And this Hurst coefficient also have a relationship with the little d parameter I mentioned previously. And d is the notation we use in the autoregressive fractional integrated moving average. So first, I'm going to estimate this auto covariance. So here I will have my sample mean, and this is the representation when L greater than or equal to 0, and here is the L less than 0. I need to consider them separately because I have functions. Unlike in the univariate cases, I could just multiply by 2, but in the case of multivariate or functional data, I can't, because X transpose X is not the same as X times X transpose. So the estimation of long-run covariance depends on knowing the memory parameter alpha, but in practice we don't. But the good thing is the first term, where we have 1 over n power 3 minus 2 alpha, it's really just a constant, because alpha is a scalar. And so this is a constant, so it really doesn't affect the eigen decompositions we're going to perform. And we're going to use the first eigenvalue and eigenfunction. This is what we mean by dominant subspace of functional data. So what we're going to do is we have this estimator where we don't worry about the constant part in front. So this is what left here. Now the selection of L, and how do we select L, and how many lags do we include? This is a really important problem. Should we include everything up to n, or should we actually truncate it to a smaller number? So it's important to obtain an optimal value of L so that we can achieve the minimal value of mean square error. And in this reasonably old paper, and we basically took a simple approach. We like L to be the minimal between the sample size n and the number of discretized data points in a curve. If a curve has 101 data points between 0 and 1, P equals to 101, okay? And it's the number of curves, so we're taking the minimal for the L. This may not be necessarily a good approach, but nonetheless, it's computationally fast. A better approach, in my view, is to use a kernel sandwich estimator, and where we have this W as a kernel function or weight function, and L is the lag, and H is the bandwidth. So it's a smooth decaying function rather than just a linear decaying function. So that's the difference between the two. And Q here is the support of order. And there is a really nice paper by Don Andrews in 1991, Econometrica, where he presents Q equals to 1, Q equals to 2 for 4 different types of kernel functions. And in this paper with Greg, we propose a plug-in algorithm for determining the optimal bandwidth H. And once we have estimated this H, and then we'll be able to approximate this long-run covariance. So this is how we're going to do it in this talk. Now, we're going to use a KR expansion. It will become clear later. And how do we represent this? As we have a realization of functional data. That is the simple mean and then plus a bunch of principal component scores and principal components. And if we have infinite many, or if we have up to n, and then we can get exact. If we truncate it to a smaller number, and then we have approximate. Now the question is, given your, well, I am using the first eigenvalue, is that really enough to capture the information in the data? So this is a key question. So the eigenvalues, once we done the decomposition, either to the variance operator or to the long-run covariance operator, and the eigenvalues will be ordered in a decreasing manner. The first one tends to be the most important in the literature, and it is the one which we're going to focus on today. And not only we focus on that, also there is a relevant work on unit root text, and they're also going to use the first set. And by using the first set, we simplify the problem from a functional data to a univariate data. So in a sense, now all of a sudden we can use all those memory parameter estimates in the univariate time series all of a sudden. So it relies on these FPCA decompositions. Okay, now if it's not enough, another thing we tried is to take the LT norm of the first few principal component scores selected using eigenvalue ratio criterion that I will talk about later in the talk. So by taking the LT norm of those principal component scores, it also allows us to reduce everything to a univariate time series. I know that the principal component scores is the one that has the T indices. So this is captures all the temporal dependence in the data. And this phi here, in a sense, it doesn't have any temporal dependence. Okay, now I'm going to talk about the memory parameter estimates. There are three categories of the estimators. The first one is a regression-based heuristic approaches. And the second one is the one which I personally like the best, is the semi-parametric. They don't require to know a specific form. In some cases, we do rely on Gaussian assumption. And I will show you the local veto estimator in this talk. So there is log periodigram, very popular by John Giewicki's work in 1983, and local veto estimator by Peter Robinson in 1995. In frequency domain, log periodigram is like ordinary least squares, and the local veto estimator is like the maximum likelihood estimator. So in the first one, we have the regression based approaches, and those are their possible approaches to my knowledge. Among all those six, I really liked Peng's method, also known as method of residuals. And this simple approach based on partial sum and blocking. So you segment your univariate time series data into different blocks, and then you take the partial sum and then do the regression. These ideas very simple. They tend to give us a pretty good estimate of the memory parameters. So Peng's method is my favorite in the category of regression based. The log periodigram is another group of estimators. Some literature also refer to GPH estimator, but there are more than just GPH estimator. However, this is one of the most popular ones. And the one which I will be focused on today is local veto estimator. This one, we have an empirical periodigram to estimate, and then we do that for all frequencies. And then if you like Carlos Vadasco's paper, and then he will use this tapering, where we select a few frequencies, not every frequencies. And then if we have an exact form for the empirical periodigram, and this gives rises to generalization of local veto estimators. And sometimes you could have outliers, so this gives rises to modified local veto estimators. Okay, so in this paper, I compared all those estimates that I mentioned above under stationarity setting, and look at the variance, the square bias, and mean square error. And based on the mean square error alone, the Pons method and the local veto method are the recommended ones for the data generating process I talked about at the beginning of the talk. So today I'll be focused on local veto estimator, but once I present the bootstrap algorithm, it can work for any estimator, even they may not have asymptotic results. So the local veto estimators is given here. It's a very brief introduction, revision of the local veto estimator. So what we have is a univariate time series. In this case, it's the first set of principal component scores. And then what we then do is we perform a discrete Fourier transformation. And then we have everything in this frequency domain, where lambda is the frequency. Now, once we have this discrete Fourier transform, we then compute the empirical parallelogram. This is given by I lambda. The reason I have a sub-indices 1 is just to remind myself I'm only taking the first principal component scores. Now, in order to obtain the estimate of the memory parameter D, and then I need to firstly define objective function. My objective function is this G function that is a positive constant, bigger than 0, less than infinite. M here is like a bandwidth parameter. It's a parameter that we need to select. I will define M shortly. But this G function depends on D. We don't really know D. We need to estimate D. We also need to estimate G iteratively. Okay. We do know this empirical parallelogram, and we do know the frequency lambda. What we don't know is the D and the G. Once we have an estimate, no matter it's good or bad, we plug this G hat into this expression. And this is the expression we're going to use to optimize D. And we do that a number of times until those two values converge or do not change up to epsilon, and then we stop the algorithm. Now, the important thing is this M parameter. How do we select M? And M tend to be dependent on the sample size N, and in the literature, there are different power. So I took 0.65, some literature use 0.7, 0.8, they all exist. I think Peter Robinson has a paper where he talked about the lower and upper bound. So long you have this power lies within the lower and upper bound, then it will be fine. So I will take 0.65 in the top. So we do that iteratively to update our G and to update our D estimates. Now, in this recent work, we also showed asymptotic results or distribution results for the local veto estimator. M here is the tuning parameter here before. And then D hat is what we estimate, and D is the truth that we don't know. It has asymptotic distribution. It's a normal, which means 0, and the variance 1 on 4. And based on that results, we can write down the upper and lower bounds for the confidence intervals. So D hat is our sample estimates based on sample, and then we also have this part is really from the asymptotic distribution above. And Q here is the quantile function of a standard normal distribution. And alpha is a level of significance. We consider the 3 levels of significance in the simulation shortly. In this construction, the parametric confidence intervals are symmetric. As you can see from here, and the differences is really just based on the quantile of the standard normal distribution. So there's symmetric centered at D hat. Now, when we're doing the bootstrap, we don't have to have a symmetric confidence interval. We could have unsymmetric confidence interval. So that's another plus for a bootstrap approach. So I'm going to talk about the Sieve bootstrap now. This is the second part of the talk, where I present an algorithm that allows us to bootstrap the functional data, stationary functional data, and with the bootstrap samples, they mimic the dependence of the original data. So in my view, bootstrap can only mimic the dependence of the original sample. And if our sample is not a good approximation of the truth, then the bootstrap doesn't work. And what we hope is the original sample is a good approximation of the truth, and therefore the bootstrap will work. So the Sieve bootstrap begins by taking center data, we subtract the mean, and then we work with the center data y. And then or using KL representation, we can write that in terms of functional PCA decompositions. In practice, we don't take infinite, we take up to k. So this is the value we need to select. And here is my principal component scores that has time indices t. And this is my basis function. So here I don't worry about my continuous variable u, but you can put a continuous variable u if you like. And here is the residual component, which are those components left out. Now, in terms of selecting the number of components, it deserves a lot of attention in the literature. And my personal favorite, by no means it's unique, but nonetheless is the one which I tend to use is this criterion based on successive eigenvalue ratios. So if k equals to 1, what we're taking is the ratio between the second eigenvalue in the sample estimate divided by the first eigenvalue in the sample estimate, multiplied by this indicator. And the reason I have this indicator is I want this ratio to be greater than a small positive number. They don't need to, I don't want them to be too small. Yeah, so that I have these binary indicators. If it's too small, I'll add this penalty. I add this penalty, so this will give value 1 if it's less than tau, and tau I will define how to select shortly. So I do that for Kmax. So there is a definition for Kmax shortly. So tau here is a small positive real value. Here is the binary indicator function. And the Kmax in this talk, I was simply just taking all those eigenvalues estimates that are greater than the mean of the eigenvalues estimates. So I count how many eigenvalues that are greater than or equal to the mean. The tau here is a small positive real value number, and I simply take 1 over the natural log of the maximal between the first eigenvalue and the sample size n. So, and then once I select my k, and then I can do my PCA decomposition using sample variance. Now you may be questioning is, why don't you use auto covariance in the long run, covariance you've been talking about? You could. Long run covariance is a nice way of summarizing informations. So if you want the most effective way of doing dimension reduction, long run covariance is a good criterion. But if I'm just going to do a dimension reduction, I don't really care about how large k is. And by doing that for the variance operator, I can achieve almost the same accuracy. I just my value of k tend to be larger. So in this Sieve bootstrap, I'm just simply using a sample variance operator. And don't worry about the kernel sandwich estimator I mentioned previously. The kernel sandwich estimator uses plug-in algorithm, so it tends to be slow and computationally infeasible when we're doing a large scale of simulations. So I'm going to do a PCA on this sample variance operator, obtain my orthonormal eigenfunctions. And then also have my principal component scores associated with those orthonormal eigenfunctions. And those k-dimensional vector or matrix of principal component scores really has the temporal dependence in them. I like to catch them using a VAR structure. One could use VMA, VAR-MA, but VAR by far is the most simplest methods to estimate the temporal dependence in the multivariate framework. Now, another question you may say, why did you use univariate time series? Because principal component score are uncorrelated. You could using univariate, but you're going to miss the dependence across, you're going to miss the cross dependence. By that, I mean the first principal component scores at time t and may correlate with the second principal component scores at time t plus 1. And therefore, by using a VAR structure, it seems to be more adequate. So A here is VAR matrix. So this is going to be estimated from sample. And then beta is our principal component scores, and they could be k-dimensional. K here doesn't have to be 1. E here is the order of VAR. And E here is the residuals. The order P can be estimated using the ICC or other criterions. Now, once we have this formulae, we're going to use this formulae to give us the bootstrap samples. Another feature about VAR is autoregression, so it requires a burn-in period. So for the burn-in period, I'm going to take the first 100 observations. So I'm throughout the first 100 observations and keep the rest. Now, the star is the bootstrap samples. So those are the bootstrapped version. This A is estimated from the sample. I don't change that. Now, the starting values up to order P, where P is the order of VAR, is going to be the same as the sample estimates for those k-dimensional principal component scores. The bootstrap residuals ET star is going to be ID resampled from centered residuals. So the centering is really important. Okay. Now, using KR representation or expansion, we obtain our bootstrap samples. This is the estimated mean. This is the fixed principal components. And this is the bootstrap principal component scores. This is the bootstrap model residuals. And that will give us the bootstrap pseudo samples. So these residuals are those terms that do not include in the first K of principal component decomposition. They're what I call model residuals. So I'm going to ID resample from centered residuals. The first 100 actually going to be discarded because of the burn-in period. Now I'm going to do an example. So here is FAR1 and the FARMA11 for those two data generating processes used previously. And the right dot is the estimated based on sample size of 250. So N is 250, relatively small. And then the cross is the true value, 0.2. So you see how far they are. It's maybe because the local veto estimator is not optimally tuned, but it's just simply because the sample size too small in my view. Now the blue ones represents the lower and upper bound for 80%, and the green one is the 80%, the blue one is 95%, and the cyan is the 99%. So this is using the asymptotic results for the local veto estimator. So it's symmetric around the sample estimates. Now, this is the bootstrap version. So we have our sample estimate, we have the true value, and this is the 80%, 95%, and 99%. Okay. And here is for FARMA11 example. Now I'm going to assess the accuracy of the interval. So I need to define a criterion. My criterion is based on empirical coverage probability. The empirical coverage probability is to count how many times my true value that I hold out lies outside the bounds. So if it lies outside the bound, either upper bound or lower bound, this will give value of 1. And I count how many times it will give me the value of 1. And so this is going to be a proportion. And then once subtract that proportion is the empirical coverage probability. Now the upper bound and lower bound are going to be different because I have alpha here controls that. So if alpha is 0.2, my bounds tend to be narrower than if alpha is 0.01. Alpha is the level of significance. Okay. R here is 200 replications. So I'm going to do 200 pseudo-random samples. And it's just because of the computational time. So I will focus on the 200. Now, another criterion I use is the CPD, which is absolute difference between empirical coverage probability and nominal coverage probability. So for the data generating process I talked about at the beginning, so these are the results for different value of D from 0.05 to 0.45. So I only consider the long memory dependence from weak to strong long memory dependence. In the second data generating processes, I will consider where D can be negative. But for this example, what I'm trying to say is the asymptotic way of constructing confidence interval does not perform as well as the Sieve bootstrap. Okay. There are some exceptions, especially when D is pretty big, like 0.4 and 0.45. The coverage probability is pretty good. In those cases, it's because the confidence V's are quite large. And then if alpha is 0.01, they're pretty close to the optimal. So those are the exceptions. But if I'm taking the simple mean over those cases, what I'm trying to say is the bootstrap one tend to perform better. This is for 500. For 500, as you can see, for the asymptotic ones, and for the bootstrap in general, they tend to improve as sample sizes become larger. Okay. So this is 250 sample sizes for functional AR MA11 with a fractional order differencing. So it's the same story. So up to about 0.3, here the performance is not that good for the asymptotic results, whereas for bootstrap, it seems to perform reasonably well, even though as D increases or as D getting larger and larger, and we see there is an increase in the CPD slightly. Now this is for 500, as sample sizes increases, they tend to reduces the CPD. One thing is because we can estimate the D hat reasonably accurate. Another thing is the construction of principal component scores seems to be more accurate too. The second data generating process is in this paper in Biometrica, and it's by Richard Davis and David Hart. It's based on fractional noise processes using autocovariance. So we start by defining autocovariance gamma J, where J is the lag variable. And H here is the Hertz coefficients. We have 0.2, which means D equals to minus 0.3. And H is 0.8, that means D equals to positive 0.3. So it reflects three scenarios. The first one is the negative dependent when D is negative number, and short range is when D equal to 0, and long range is when D greater than 0. Now, once we have those gamma J's, and then we're going to build our discrete Fourier transform from those gamma J's. So we define GK. This is encompasses gamma 0 and gamma n as well as a bunch of grammars that between 1 and -1. So we chose this form because they represent or mimic the discrete Fourier transformations. Yeah, okay. Now, once we have those JK, and then we're going to go one more step by introducing some noise to it. We have the eta 0 and the eta n and the eta k. They are the standard Brownian motion, just like in the first DGP. The function support is also unit interval, and in this way, we can construct our functional curves. We consider 2 sample sizes, and also with R equals to 200 replications. So this is the results, and we have 3 levels of significance, and we have negative dependent, and short range, and long range dependent. And what I guess trying to say is the bootstrap of those 3 columns perform better than the asymptotic results. One common is as sample sizes become bigger, and we see the asymptotic results tend to improve, which is a really nice thing. Another comment I like to make is when in the long range dependent cases, by using the asymptotic results, they tend to be actually better than the bootstrap ones. So this is a weird phenomenon which I try to understand. So our bootstrap one seems to be not as good as the asymptotic results when we really have the long range dependent for those 2 cases in the bottom 2 rows. But overall, if I'm taking the mean over all those 5 scenarios, they represent overall assessments. So in summary, I present an asymptotic way of constructing the memory parameter. And the way of constructing that is parametric based and isometric, centered at estimated value of d hat. And this asymptotic results only available for selected range of memory estimators, not for all. There are estimators I listed before, they don't have the asymptotic distributions yet. But in contrast, the Sieve bootstraps allows us to bootstrap data, and then we can use that and to estimate the memory parameters for any estimators. So this is really the nice thing of the bootstrap methods. One thing I always trouble myself is the optimal selection of M. So in this talk, I'll talk about M equals to n power 0.65. Of course, there could be other way of selecting this M. So I'm simply just taking one of the many approaches. So with that, I will finish my talk. I'd like to thank Thomas and Alex for organizing this workshop. I'd like to thank audiences to listen to the talk. And here is my email and also a ResearchGate if you like to look at some recent works. So thank you so much.
Thank you, Hanlin, for a very interesting talk. If you have any questions, please feel free to post it in the chat. So Francis has a question asking about were your Sieve bootstraps confidence interval percentile CI or something else?
Were your Sieve bootstrap CI percentile CI? Yes, it is a non-parametric. Yes. So the way I'll do it is I bootstrap it, and then for each bootstrap samples, I'll apply the local veto estimator, obtain the d hat, so or d star. And then if I have 400, I do 400 bootstrap replications. And if I have 400 of them, I take the percentiles. Yeah, thanks.
Okay, any other questions? Okay, maybe I'll ask one. Okay, first is another one for asymptotic CIs. Are they guaranteed to be within the minus 0.5 to positive 0.5 range?
Yes, yes. So in the local veto estimators, you can set the so-called admissible range. This admissible range is user-defined. So I restrict myself in the stationary world because I simulate data that are stationary. But you're absolutely right. If we have non-stationary data, the range will be different. The range could be up to 2.5 in some cases.
Okay, hopefully that answers Francis' questions. Anyone has any other questions? Okay, maybe I have one. Maybe I missed something as well. In selecting the K, I think, with the tau that you chose, I don't quite understand why K. Is it the lambda K plus 1 on K?
Hold on, I was just trying to bring it up for the benefit of everyone. Yes.
Oh, it's lambda K. Okay, I misread it. It's lambda K greater than lambda 1. Okay, thanks. I think I missed it. Yep.
That's okay.
Yep. I think it's looking at consecutive lambda values. So that's why it doesn't make sense to look at to be greater than any positive real number. So I just misread it. Thanks, Hanlin.
It's okay. I think one comment I like to make is the eigenvalue ratio. They tend to be better than taking the difference. So taking the ratio is the better way of doing it. There are other criterions nevertheless. Yeah, but this is just my personal favorite.
Cool. Okay, so any other questions? Okay, if there's no other questions, then please join me and thank Hanlin again for a wonderful talk.
Thank you, Thomas.
It's a pleasure.